S237 is a course about the physical structure, chemical composition and evolution of the Earth. What we'll be doing is building up models which will explain what we can see or measure, as well as describe the deeper structure of the Earth in a consistent way. In this program, we're going to paint a broad picture by introducing you to some of the evidence for the origin and the internal constitution of the Earth. And in the rest of the course, we'll be looking at the various parts of this picture in more detail. So, in trying to build up a structural and chemical model for the Earth's origin and interior, where's the best place to start? Well, the natural place to start is by considering the chemical composition of what we can see, the material of the Earth's crust. But then we come to a problem. If we're going to model layers of the Earth's interior, can we assume that the elements to be found there will occur in the same proportions as they do at the surface? You realize that this is highly unlikely because you know already that the Earth's layers have different compositions. So we must set up a theory which will explain what we know about the bulk or total chemical composition of the Earth. And the best place to start such a theory is at the beginning. We begin with a hypothesis. 15,000 million years ago, the universe began with the Big Bang. To start with, it was very hot, hundreds of millions of degrees. But as the universe expanded and cooled, first atoms, then molecules of hydrogen were created. Hydrogen, the lightest of all the elements, existed as a gas in space. Then gravitational attraction led to hydrogen becoming more and more compressed into small local regions where it started to burn, to form heavier elements as nuclei were fused together. These local regions of burning hydrogen are what we call stars. As the stars burned, they became smaller and brighter. Eventually, the most massive became supernovae. They exploded, hurtling the heavier elements, products of their fusion reactions, out into space as interstellar gas and dust. These were the ingredients for the formation of new stars, such as our Sun, which formed between 4 and 5,000 million years ago by condensation from a cloud of gas and dust we call the primitive solar nebula. The solar system condensed from the same material, but fusion does not take place in planets as it does in the Sun because the planets are not massive or hot enough. Since their formation, the Earth and the other planets have evolved in various ways, but notice that the overall composition of the planets should be the same as when they formed, apart from small changes due, for example, to radioactive decay. Now let's look at this hypothesis for the Earth's origin in more detail. The first thing to realize is that the Sun and the planets all formed from the same raw material. They all contained in this model the same proportions of elements. In principle, you might think we should be able to scoop up a handful of soil from the surface of each, and each sample would have, on chemical analysis, the same proportions of various elements. But again, things are not that simple. Let's go and look at the other planets in the solar system to see what we find. Well, we'll start here with Pluto, furthest planet from the Sun. And remember, we're looking for evidence of elemental abundances. How are we to estimate them for Pluto? Well, we know that Pluto is one of the smallest planets and that it is furthest from the Sun. It was discovered in 1930 when astronomers were looking for an unobserved body to account for the irregularities in the orbit of Neptune, the next planet in. And this is the key to our investigation of the solar system, the action of gravity. We can estimate a planet's mass by its effect on the orbits of the other planets and on the motions of its own satellites, as well as from its period of rotation around the Sun, which in the case of Pluto is 247 years. We know its size from direct observation, and so we can deduce its density. And this turns out to be about 1,700 kilograms per cubic meter. Now, to make that simpler, we can express it as a density relative to the Earth's density, which is 5,520 kilograms per cubic meter. Then Pluto's relative density is 0.3. This much lower density than for the Earth has been interpreted as meaning that Pluto is a methane ice-rich planet. Moving on, Neptune is a much larger planet, 59 times larger than the Earth in volume. This is the first of the large outer or major planets, and its relative density, similar to Pluto's, indicates that it too is predominantly made of light gases. Uranus is another gaseous planet, this time the first one with rings, and we're now 3,000 million kilometers from the Sun, and the orbital periods of the planets are getting shorter. Uranus has an orbital period of just 84 years. Now, we come to the two largest planets, and first, Saturn, whose volume is nearly 1,000 times greater than that of the Earth, but which nevertheless has an extremely low density. The conspicuous ring systems of Saturn, and of course for Uranus, comprise dust and ices, frozen particles that have not accreted into satellites. Next to Jupiter. Here we can see striking evidence of the gaseous nature of Jupiter from photographs taken by the Voyager mission in 1979. Well, we guess as much from the relative density. Jupiter has a vast volume, 1,400 times that of the Earth, and it contains 2.5 times the mass of all the rest of the planets put together. But like the other outer planets, its density is low. So it probably has a composition dominated by hydrogen and helium. Jupiter also has many moons, like a mini solar system in its own right. Well, we're now 500 million kilometers from the Sun, and the next objects we find in the solar system are the relatively minute asteroids. There are probably millions of them extending in an orbital belt around the Sun. Asteroids will play an important part in our story later because they're the most probable source for meteorites. Well, our density story continues with the next of the proper planets, Mars. Mars orbits around the Sun in about 2 Earth years, and its density is 3,950 kilograms per cubic meter, or 0.72 times the Earth's density. Now, this is the highest density we've met so far, and it's reflected by what we've seen of the Martian surface, rocky and solid in comparison with the outer planets. Mars is the first of the 4 inner or terrestrial planets. The Earth, of course, has the relative density figure of 1. Its appearance from space is deceptive. Its clouds resemble those of the largest planets, whereas in fact, it's the densest of all the planets. Venus, next nearest to the Sun, has a density 95% that of the Earth, and it too is obscured by thick clouds of carbon dioxide and other acidic gases. And Mercury, nearest to the Sun, has an intensely cratered surface like that of our Moon and Mars and Venus, indicating a history of bombardment by meteorites. Mercury is the smallest inner planet, yet it has a surprisingly high density, quite close to that of the Earth. Well, this walk through the planets leads us to some important general conclusions about the density relationships for all the planets. If we compare distance from the Sun with density relative to the Earth, we see that the planets fall into 2 distinct categories. The inner planets, Mercury, Venus, Earth, Mars, which are relatively dense planets with hard surfaces. And the outer planets, Jupiter, Saturn, Uranus, Neptune and Pluto, which have significantly lower densities and are generally light and gaseous, though they may have small rocky cores. This shows that our hypothesis that all the planets were formed from the same materials must be modified, and an understanding of their different densities, and therefore their chemical compositions, comes from a study of the composition of stars, or more particularly, the Sun. The Sun has a density comparable with that of Jupiter or Uranus, but in other respects the Sun is very different because it's a star, and it's hot, 6,000 degrees at the surface. The fact that it radiates energy allows us to examine its composition. Most of what we know comes from the study of the solar spectrum. This is a continuous emission spectrum crossed by dark bands, the Fraunhofer lines. These lines come from the absorption of particular frequencies of light in the continuous spectrum by the sun's hot atmosphere. And each of these frequencies characterizes an individual element. For instance, here are some of the lines corresponding to magnesium and iron. Now, we can determine the relative strengths of these absorption lines by photographing the spectrum for different lengths of time. And from this, we can build up a picture of the relative abundances of the elements in the solar atmosphere. For the most part, we think these are the same as their relative abundances in the sun itself. And what do we find? If we plot atomic mass number against a log scale of relative abundance, compared with silicon, which is set at 10 to the 6 atoms, we find a profile like this: immense amounts of hydrogen and helium, and much lower amounts, totaling only 2% of the mass, of the heavier elements. But there's a series of peaks, notably corresponding to carbon, oxygen, magnesium, silicon, sulfur, and iron. And we can explain these peaks by looking at the processes taking place at the heart of all stars, nuclear fusion. In the simplest form of fusion, two hydrogen atoms fuse together to form helium, giving off energy as they do so. And that, by the way, is the origin of sunlight. If that was the only process in the universe, all matter would consist of just hydrogen and helium. But this is just the first in a chain of such fusions. Helium atoms, in turn, can fuse to form carbon. They combine with carbon atoms to produce oxygen, oxygen plus more helium to form magnesium, and so on. Right up to iron. But for each of these fusion reactions to occur, increasing temperature and pressure are needed. In our sun, only the first of these steps is happening. This is why the ratios of all the other elements are the same as they were at the time of the primitive solar nebula. All the elements heavier than helium in the sun are the remains of fusion processes in other stars larger and hotter than the sun, whose remains formed the primitive solar nebula. And their relative proportions were fixed, not just in the sun, but throughout the solar system before the planets formed. So we know what was in our primitive solar nebula from looking at the spectrum of the sun, and we can begin to look for similar proportions of elements elsewhere in the solar system. One encouraging sign is the similarity of the sun's density to those of the largest planets, and this suggests that they may have a lot of hydrogen and its compounds in their compositions. This is not so for the inner planets, though. But what about their proportions of heavier elements? Many of the rocks of the Earth's crust contain elements such as silicon and oxygen, two of the abundant, heavier solar elements. But the overall density of the Earth is even greater than that of surface rocks, and so we must look deeper inside the Earth. Remember, we want a model to explain the bulk composition of the Earth. And we can't get any further without saying something about the structure of the Earth, which involves looking at the passage of seismic waves through our planet. Well, let's suppose an earthquake occurs here, right at the back of the Earth from your point of view. Now, the Earth will transmit shock waves from that earthquake, and a seismograph anywhere on the Earth's surface will record waves arriving sometime after the event. Anywhere? Well, not quite. As a zone looking rather like a donut in which no seismic waves will arrive from this event. Why is this? Well, if we open up the Earth, we can see why. Imagine another event here. Shock waves are refracted through the Earth in curves like this, which we can deduce from the time it takes for them to reach seismographs here, here, and here. But there are no arrivals in this region, the shadow zone you saw earlier, and we take this to imply the existence of a high-density core at the center of the Earth, which refracts the waves from our seismic event so that they emerge on the far side of the shadow zone, down here. In fact, Detailed study of earthquake waves throughout the entire Earth, which you'll find described in Block 2, have enabled us to build up an accurate picture of the variation of density, in kilograms per cubic metre, against depth, in kilometres, from the Earth's surface. It looks like this. As you can see, there are three distinct regions of different density. The mantle, down to a depth of 2,900 kilometres, the outer core, where we have sharp increases in density, and the small, slightly denser inner core, right at the centre of the Earth. What then does this tell us about the composition of the interior? Well, we can use the density depth curve to say something about the elements that are likely to be present in each layer. But of course, so many elements could be present in each layer that there's a great deal of ambiguity in simply deducing composition from density. So what we need is additional evidence of the sorts of elements and compounds which might make up the Earth's interior. The solar spectrum has suggested the elements, ignoring the lightest ones, but we need to know what compounds they form, and we deduce these from a study of those all-important extraterrestrial samples of rocky material, the meteorites. Remember that meteorites are thought to be fragments of the asteroidal mini-planets in orbit round the Sun between Mars and Jupiter. Like the rest of the solar system, they must have formed from the primitive solar nebula, but unlike the rest of the solar system, we have samples which have fallen to Earth. For example, this is a sample of the Barwell meteorite which fell in Leicestershire in 1965. Notice the brown metallic skin due to atmospheric heating. Inside, this meteorite consists mainly of silicates, green olivine, some metal. I can see a brown discoloration on here due to oxidation of iron. And it also contains some tiny spherical chondrules, which makes it a chondritic meteorite. Now, if we looked at a thin section of this meteorite, as in this picture, again you can see the chondrules here and here. You can see the silicate, this is olivine, these highly coloured grains, and also these dark patches in this thin section photograph are iron metal. But of course we can find out a lot more about meteoritic iron by looking at iron meteorites. And here's a picture of an iron meteorite. It's actually a polished surface. And in here you can see blades of iron-nickel alloy, iron with a little nickel, and also some inclusions of iron sulfide. So to summarize, the meteorites then contain three principal phases. They contain olivine, magnesium silicates, they contain iron metal, often with a little nickel, and they also contain iron sulfide. And chondritic meteorites, like the Barwell, appear to have changed chemically the least since their condensation from the primitive solar nebula. They contain little hydrogen or helium, but otherwise their element abundances should be similar to the heavy elements in the solar spectrum. If we plot elemental abundances in chondrites, again using silicon as a standard, the heavier elements plot like this. And as you can see, we can fit a straight line to these data very well. The further from the line an element is, the greater is the difference between the amount in the Sun and the amount in a chondritic meteorite. And in general, as you can see, the abundances match very well. Now, we've already seen the way these elements combine in chondrites, and they can be used as a model for the way in which elements might be combined in the Earth. Now, we can complete our interpretation of the density curve we showed you earlier. The density of the inner core corresponds well with the iron-nickel alloy, fractionally denser than iron. The outer core could be a fluid iron-sulfur mixture, a little less dense than iron, and the mantle has the right density for magnesium-rich silicates. In other words, the densities of these three main layers in the Earth correspond to the three main components we find in meteorites. And this means that the most important elements in the Earth are iron and sulfur in the core, and silicon, oxygen, and magnesium in the crust and mantle. Well, this should strike you as familiar. The same five elements were abundant in the solar atmosphere and therefore in the primitive solar nebula. Now, we can't prove this composition for the inner and outer core, But in the case of the mantle, there's further evidence from volcanic lavas brought up from the mantle. Nodules in these lavas have olivine, the green magnesium silicate mineral again, as their main mineral. And in the crust, the thin outermost layer of the Earth, we also find rocks dominated by silicates, though are of lower density than in the mantle. For instance, these granites contain minerals that are very rich in silica. This grey-looking mineral is actually glassy, is pure silica or quartz, and the pink grains are feldspar, which are also rich in silica. Well, to return finally to our bulk model of elements in the Earth, we can now estimate the actual abundances of the 5 most important elements in its composition. We plot abundances relative to silicon against increasing mass number for oxygen, magnesium, silicon, sulfur, and iron, like this. If we now compare these values with the abundances of the same elements in the Sun from the plot we looked at earlier, we get this. We find a very good match for iron and silicon, naturally, since we've assumed silicon to be the same in both the Sun and the Earth, and also for magnesium. But the Earth has less oxygen than the Sun, and the same is true of sulfur, and of course more so for those lighter elements than oxygen. Therefore, either these elements, including hydrogen and helium, were not accreted into the Earth and other inner planets, or they have been partly lost since accretion. For example, the loss of sulfur dioxide and carbon monoxide or dioxide from the accreting Earth could have depleted oxygen, carbon, and sulfur at the same time. The slightly lower oxygen abundance in the Earth than in the Sun is one reason why much of the Earth's iron is in the metallic or sulfide state in the core. As an exercise, perhaps you might like to think what would happen on a more oxygen-rich planet. What difference, for instance, would it make to the size of the core? You find the answer in the broadcast notes. Well, we've come a long way in this program, and yet we've only scratched the surface of planetary structure and chemistry. The important things I hope we've shown are first, the striking similarity of abundances of heavy elements in the chondrites and the solar atmosphere. Second, that this suggests that the chondrites may have formed directly from the 2% of heavy elements in the primitive solar nebula. And third, that this suggests a combined chemical and structural model for the Earth, which is borne out by structural inferences from seismology and by surface chemical data. This is the chondritic Earth model. You might think S237 could end there, but we've left a lot of questions unanswered and made very many simplifying assumptions to reach this model. We must make many more refinements before we can be truly confident that this model represents the real Earth.
When it investigates